I welcome you all for this presentation. In this presentation, we are going to discuss about block ciphers. This is the overview of this presentation, introduction to block ciphers. Then we are going to discuss about the difference between block and stream ciphers. Already block cipher is familiar to you only. We have seen some of the block as well as stream ciphers. Let us see what is the difference. Then block cipher principles, then substitution permutation ciphers, confusion diffusion, then feastal cipher, then feastal cipher design elements, followed by summary of this presentation. So what is the need for block cipher, or what is a block cipher? In the block cipher, what we are doing is we are just using the entire plain text as one block, or we are just dividing the plain text into different blocks of sizes like 64-bit, then 128-bit likewise. And those blocks we are using for encryption as well as decryption. That is about the block cipher. It is one of the most widely used types of cryptographic algorithms, and it provides secrecy and authentication services. And the main focus of this block cipher, it is this methodology is used in data encryption standard. That is data encryption standard. DES is also a block cipher, because there we are just considering the plain text entirely, or we are not considering it entirely. 64 bits of plain text we are considering. So if the size of the plain text is not 64, then we have to make it as a 64-bit, or if the size of the plain text is more than that, we have to divide the plain text into blocks of 64-bit. That is about the data encryption standard block cipher. Next, the difference between block and stream ciphers. So here the block ciphers process the messages in blocks, that is each of which is then encrypted or decrypted, like a substitution on very big characters, that is 64 bits or more, that is the block. But stream ciphers process messages a bit or byte at a time, and we are performing encryption or decryption. And many current ciphers are block ciphers only. So these block ciphers are better analyzed, and they are used in broad ranges of applications. So only here we are discussing mainly about the block ciphers. Next, what are the block ciphers we have already seen? It's a Playfair cipher. We are all aware that in a Playfair cipher we have seen that balloon example. So we have to split it into two characters, and if there is a repetition, then you have to fill it with the filler. And again, anyway, two characters are definitely needed. So we are dividing into two characters. This is a very small block cipher actually. Then some stream ciphers we have seen is the Vignera cipher. Vernam cipher we have not seen, but one time part we have seen. Vernam cipher is not a new one. It is just like Vignera cipher only, but each and every time the key we are considering is different. We are just selecting one byte, and one byte of key we are using. For each and every one byte we are using a different key. There comes the one time part. So this one time part is only providing perfect secrecy, meaning that it cannot be broken by any of the attacker, because each and every time new keys are coming in. So for the same plain text we are getting different cipher text. So it cannot be broken by any of the attackers. So this one time part alone providing perfect secrecy. Other ciphers are vulnerable to some form of attacks. But how long it is not affected, that only we have to look into. This is the pictorial representation of block versus stream ciphers. Here you see that we are having the stream cipher. We are performing processing one bit or one byte at a time. So here we are having the plain text. Then we are having the key. The key is given to the bitstream generation algorithm, so that key ki is generated, and this pi plus ki mod something we are performing. That is for Vignera and telling. For some other algorithms, different encryption we are using. Pi mod ki, pi plus ki mod 26, we are getting the ciphertext. The same is repeated here. The key stream is there and the ciphertext is there. We can extract the plain text out here. Then coming to the block cipher, we have to consider the entire plain text. That entire plain text is passed on to the encryption algorithm with the help of key k. We are getting the ciphertext of b bits. Whichever the size of the plain text, same size of ciphertext we are getting. This is the difference between the stream cipher and block cipher. Next is the block cipher principles. Here we are going to discuss about what are the principles behind the block cipher, because we are going to discuss about feasible cipher structure. So we need to know the block cipher principles. So here this one is the most symmetric block ciphers and are based on feasible cipher structure block ciphers, and we need this block cipher since we have to perform both encryption and as well as decryption. That is, if we are performing encryption, then the reverse process is also possible in order to recover the plain text from the cipher text in an efficient manner. So this block ciphers look like an extremely large substitution. Actually, you may feel that in stream cipher also we are just considering it as a block. If you are taking a byte, then we can consider it as a block only. 8 bits form a byte. But here we are performing some large substitution, 64 bits or the entire plain text. Likewise, we are just taking. So here we need table of 2 power 64 entries for a 64-bit block. Generally, we are taking a large bit blocks. So suppose if your block is 64-bit, then we have to take 2 power 64 entries, all possible combinations. Say for example, if you are having two entries in the sense only zeros and ones, then how many combinations we can have? 0 0 0 1, then 1 0 1 1, 4 combinations we can have. Suppose if you are taking 4-bit number, then we are having 16 combination, 2 power 4, 16 combinations we are having. So here instead of creating a smaller building block, we are creating a large building block here we are using, and this is the concept behind this product cipher. So these are the principles behind the block cipher. Next, this one is the ideal block cipher. Why the name ideal block cipher means it allows maximum number of possible encryption mappings from the plain text block. So here we are having a 4 to 16 decoder and we are having the 16 to 4 encoder. Suppose we are having 4 input, that is 0 0 0 0. Then how many possibilities are there? 2 power 4 equal to 16. So only 4 to 16 and 16 to 4 encoder as well as decoder we are having. So this only we are calling it as the ideal block cipher. And one more thing we have to think is whether it is reversible or irreversible. That also we have to think. If it is a reversible case, means we can easily convert from the plain text to the cipher text and cipher text to the plain text. But if it is a irreversible, say that means for any plain text, if you are having two different cipher texts, then it is a irreversible case. This is the ideal block cipher, that is it allows maximum number of possible mappings for the plain text block. Next is a substitution permutation ciphers. We already know that we can have some hybridization like substitution followed by substitution, substitution followed by permutation. But if you have substitution followed by permutation, then the security providers is more compared to just a substitution or just a permutation or substitution and permutation. So this Claude Shannon introduced this idea of substitution permutation networks, and it was given in a paper in the year 1949. See how old was this concept, but now also we are discussing, because these are the foundation for all the crypto systems. So only we are discussing now also, and this paper only formed the basis of the modern block ciphers. So we know the classical cryptography, some combination or hybridization of the classical we can use in the modern cryptography. So this substitution permutation nets are based on two primitive cryptographic operations, that is substitution and permutation. Later on in the coming algorithms and all, we will be calling as S box and P box only. You have to know S box means it is a substitution box and P box means it is a permutation box. And why we are having this hybridization? In the sense, we need to provide more confusion and diffusion. That is, we have to irritate the attacker, because if it is easily findable means he will enjoy, right? The attacker will enjoy. But if the answer is not coming means we are just frustrating or irritating the attacker. So we have to irritate the attacker in a very good manner so that our crypto system is not vulnerable to any attack. So we have to provide we have to come up with such a crypto system. So we have to provide confusion and diffusion of the message and the key. Let us see what is confusion and diffusion. It is a very important terms in this cryptography. Confusion means we are making a relationship between ciphertext and key as complex as possible. So we are making a relationship between ciphertext and key as complex as possible. That is the confusion. So if you are making a relation, so if you are making as complex means we can't decrypt. By getting only the ciphertext, the attacker can't get the key in order to find out the plain text. So we are making a relationship between ciphertext and key as complex as possible. That is, we are making some confusion. Generally, confusion means we are unable to decide something, right? So here also with the ciphertext and key, we are making so many confusion so that the attacker can't come to any conclusion that we can create the we can hack or we can break the crypto system in this way alone. Likewise, they can't come to the conclusion. And another term is diffusion. That is, diffusion in the sense it dissipates statistical structure of plain text over bulk of ciphertext. Statistical structure of plain text over bulk of ciphertext. That means each plain text digit affects the value of many ciphertext digits. Suppose if you are changing one of the bit in the plain text, that change will affect many ciphertext digits. If it is a case, then this crypto system is not vulnerable to attack, not easily vulnerable to attack. So this way we can take it. So the cipher needs to completely obscure the statistical properties of the original message. And main thing, if you want to use this confusion and diffusion means the one-time pad surely did this. Other than that, we have to think. And it is a more practically Shannon suggested combining this substitution and permutation elements to obtain by using this diffusion and confusion. So we are just mixing up substitution and permutation. There itself we are making so many combinations and it is very difficult for the attacker to break the crypto system. So confusion and diffusion are very important. Confusion means you have to remember that ciphertext and key. See, so ciphertext and key. Diffusion means plain text and ciphertext. If you change one digit in the plain text, it may affect many bits in the ciphertext. That is the diffusion. Next is the very important structure, that is the Feastel cipher structure. And this Feastel cipher structure was devised by Horst Feastel. So the inventor has given his name for the cipher. So in many of the ciphers, the authors or inventors only are giving their own names. So we can also see some of your names in the cipher in the future. So here, this Feastel cipher structure is based on the concept of invertible product cipher. So here what we are doing is we are partitioning the input blocks into two halves. And we are processing through multiple rounds. First, plain text is given, some 64-bit plain text is given. We are dividing into left half and right half. Then we are performing encryption with this left half and right half with some combination of operation we are doing. And here we are having many rounds of the same operation. Why we are doing many rounds of the same operation means in order to provide more confusion and diffusion only, we are performing many rounds with the same operation. So here we are processing through multiple rounds which perform a substitution on left data half based on the round function of the right half and the subkey. Then we have the permutation, that is swapping halves. After some rounds, that is 16 rounds, we are having the permutation also. So this concept was implemented in the Shannon's substitution permutation net concept in 1949. So this is the pictorial representation of the Feastel cipher structure. Here you can see that totally we are having 16 rounds and each and every round the same operation is performed. So the same operation is repeated for 16 rounds. And how? Let us see one round. First, the plain text is divided into left half and right half. Here L stands for left and R stands for right, and here E stands for encryption. Encryption 0 to we are getting encryption 16. So initially we are having encryption 0. Then finally what we are doing is we are having the left encryption 0 and that is passed on to the right encryption 0 also. We are assigning that the last to left encryption 0 and the last to right encryption 0. That is from reverse order we are getting in the decryption part. Finally, we have to get the plain text, right, after decryption. So only here we are getting the result as LE0 and RE0 after 16 rounds. Here on first round, here you can see that left encryption 0, that plain text, left side of the plain text is given to the encryption function. Before that, we are just passing the right encryption to a function called f of r comma k1. R comma k1 in the sense r is the right half of the plain text and k is the sub key k. And you can see the difference. Each and every round we are having different key. These keys we are calling it as sub keys. So the sub key generation process itself, it is one big technique. So we are initially we are having one key size, then from that key size we are dividing into different sub keys, and we are using each and every sub key for the various rounds. So here we are having the function, in the function, this function we are calling it as a round function. There also we are performing some computation only. Later on we see what is that, what operation we are doing or performing with this function. Now for knowing the feastal cipher structure, just you have to know what are the parameters we are passing. Only R, E of 0, E0 and K1 only. In all the other rounds we are passing R and the corresponding sub keys. Then what we are doing, this directly this R is passed on to this one. Here we are just swapping it, that is LE1. Then the result we are calling it as RE1. Then again directly RE1 is replaced with LE2. Likewise it goes on. Finally, after 16 rounds, you see here one swapping happens. Here only we are applying the permutation operation. LE17 and RE17. Just swapping we are just doing. Then what we are doing is, in the decryption part, we are assigning this RE16 and this LE16. And what we are doing is, with this operation only we are performing all the decryption. And finally, whatever is in the RE17, that we are assigning here in the output part of the plain text, whatever we are having, that we are getting here. RT17 equal to LE0, then LD17 equal to RE0, which is equivalent to this value. That is the plain text. In the DS, while discussing DS, we can see with example also. So far in the classical cryptography, we worked out many problems manually. But here we are just taking 64-bit plain text. So doing it manually is somewhat difficult. But we will solve for some small plain text and see how this each and every step is working. It is very difficult to solve the entire operation. But 1 or 2 rounds we can perform and we can see the results. Coming to the feastal cipher design elements, we are having the block size, key size, number of rounds, sub-key generation algorithm, then round function, F, there we had one F, that is the round function. Then fast software encryption or decryption, ease of analysis. Let us see one by one. Coming the block size, the larger block means we are providing greater security. So only here in the block cipher, here we are using 64 bits. Then key size, it is 56 to 128 bits. And number of rounds in the feastal cipher structure, it is 16 rounds. Sub-key generation algorithm, if we are providing more complexity, then security analysis is very difficult. So greater complexity should lead to greater difficulty of cryptanalysis. So breaking the system is also very difficult for the attacker. Then round function, here also if you are providing greater complexity means greater resistance to cryptanalysis. So it is not that vulnerable to attack, but anyway it is vulnerable to some form of attack. Next is fast software encryption decryption, that is the speed of execution of the algorithm is very much important. So if you are going for the 16 rounds, what is the time taken to execute? But if you are not going in for 16, then the security becomes a question. So how they fixed 16 rounds? Why not 17 or 18 or 15? Means using some trial and error only, the inventors of this algorithm, they fixed to 16 rounds. And ease of analysis to be able to develop a higher level of assurance as to its strength. And for the decryption, we are using the same algorithm with the reversed keys. So these are the cipher design elements in the feastal cipher structure. So in this presentation, we discuss about introduction to block cipher, then the difference between block and stream ciphers. Then we discuss about the block cipher principles. Then we discuss about the substitution permutation ciphers. Then what is confusion diffusion, very important terms. Then we discuss about the feastal cipher structure as well as the feastal cipher design elements. The next presentation we will be discussing about data encryption standard which uses this feastal cipher structure. Thank you.